All right. So a couple of practice problems for stoichiometry. This happens to be the review guide. I believe most of these equations are balanced for you already, but we're going to go through just a couple of examples just so that you have a couple more things to reference as you're kind of going through yourself and studying for the upcoming stoichiometry test. So for the first portion of this, these are more the, I guess, what you would call straightforward or more basic stoichiometry problems. They are just going from substance A to substance B. And of course, depending upon the unit that you're given, it's going to be where you are at on your bridge. In this case, we get mass of A, and we know it's A because we get that starting amount there. And then we have moles of B, right? No, we want to make sure that we know that B is just a different substance than A, what we start with. And then the unit. The unit is incredibly important because it tells you where to start and where to end. So in this case, we are going from mass of A to moles of A to then moles of B, and then we are stopping. So this is going to be a 2-step problem. So a way that you can set these up is, remember, units and substance always. And before I even put anything in, I'm just going to set up my nice little table or my fractions for dimensional analysis and all that for 2 steps, right? And these are the 2 steps that I'm going to need. And now I'm going to fill in units. So I know that in regards to the units to cancel out, they need to appear diagonal. So I know grams of CO2 go down here and moles of CO2 go on top, right? That's mass to mole for substance A. And then the same thing's going to happen over here, right? The moles as a unit go down here for CO2, and I'm going to moles of B, which is, in this case, Fe2O3. And I know that I want moles of Fe2O3 in the end. And look at that. That's half credit right there just by setting it up correctly. And now we can go back in and put in those number values. So, of course, grams to mole is the molar mass of CO2. I find that from the periodic table. You take 1 C, you add it to 2 O's, and that is a total mass of 44.01. 1 mole here on top, that's what molar mass is always equal to. And then this step right here, mole to mole, you use the coefficients. You don't see a coefficient in front of there. That means it's 1. There's a 3. There's a 3. There's a 2. And now we just look, hey, what number is in front of the CO2? Oh, that's 3. What number is in front of the iron oxide? Oh, that's 2, or that's 1. There you go. All right, and that's where I stop. That's what it's asking me to find. So then I go through and hopefully, there it is. I calculate. You saw a beautiful historic relief field there. I like doing it all at once, just multiplying numbers on top, dividing by bottom. So I start with the 102.3. I divide by 44.01. Notice I'm not multiplying or dividing by the ones if I have them because it's just going to be what it is, right? And then divide by 3 because that's also on the bottom there. I end up with 0.77. So over here, I'm going to put 0.77 hundredths place, please, at least for precision purposes. So that's good there. These are extensions of that problem. So in this case, I'm given the mass, or I want the mass of Fe, which is mass B. So this problem would be a mass A to moles A to moles of B to mass of B problem, right? In this case, we would have to go with that extra 3rd step. So this is 1 step, this is 2 steps, and this would be 3 to get to that next quantity or amount that we want. So there'd just be another addition onto our dimensional analysis table or train, whatever you want to call it. So a lot of these are very similar, leading up to kind of some of the limiting reactant stuff. Just note that anytime you have liters, like in C there, Liters is volume, so in this case, for this set of problems, this would be volume of B, hydrogen gas, and remember it's H2, right? So on and so forth, would react this many. So I have G, which is grams, so I know it's mass of A. That's a starting substance, right? So just making sure that you're annotating so that you know where you need to start and where you need to end on the mole bridge. That helps limit the amount of extra steps that you take. Down here, this is pretty much like the ice cream sundae example. We have 6 pieces of bacon, 2 tomatoes, 1 piece of lettuce equals 1 BLT, right? This is the recipe for it. I cannot make a BLT if I don't have 6 pieces of bacon, 2 tomatoes, and 1 piece of lettuce. So how we do this, and I'm going to just write it out. We have 6 bacon. And I know that there are, oh, I'm so sorry. That's the recipe, all right? Don't do what I did. Here are the amounts. So we have 24 pieces of bacon, and I'll do it more so like I did in class. 24 pieces of bacon. We have 10 tomatoes, and we have 40 pieces of lettuce. And what we're going to do is we are going to start with those amounts, right? So 24 pieces of bacon. And now I know that based on my recipe, there are 6 pieces of bacon for every 1 BLT, right? And I do this exact same process with each reactant, just like I did in the limiting reactant stuff in the notes and in the 08 worksheet. 10 tomatoes, 10 tomato. I know that for every 2 tomatoes, I have 1 BLT, right, based on the recipe. And last but not least, I have 40 lettuce. All right, and now one of these is going to run out first. One of these is going to run out first. I know that there are 1 lettuce, for every 1 BLT. So what we're doing is similar to the method that we did, the last class we met during the beginning of our review day, where we're taking all of the amounts of the starting substances, whatever the reactants are that we have, right? These are like the reactants. And the BLT is, in this case, just 1 product. Right, those are the products. And then we're just going to figure out how many BLTs should I be able to get based on the starting amounts of those ingredients. In this case, I see 24 divided by 6 would be 4 BLTs. 10 divided by 2 would be 5 BLTs. And 40 divided by 1, that would be 40 BLTs. Now, I look at those numbers and I see which one is the smallest amount, because that's going to be produced by the one ingredient that we have at the beginning that's going to run out first. It's going to limit the amount that we can make. So I look, I compare all of these, and I see, and I see that 4 BLTs is the smallest amount that's there, which means I can make only 4 BLTs and no more. Because once I create those 4 BLTs, I have run out of bacon, which tells me that bacon is our limiting reactant, whereas both the tomatoes and the lettuce are now the excess. They're excess because I have more than I need, right? And the whole idea behind this type of analogy is so that we can then more accurately or more easily figure out, okay, when we start with 2 or more things in terms of an amount, one of those is going to run out first. So we have to figure out which can make the least amount of product, and I can make no more than this. So 4 BLTs, this is the amount of product we can make. Right? That's the amount of product that we can make. So it's always the smallest one. So bringing into this last example that I'm going to do, Always remember to balance your equation. So it'll be time for the calculator soon. I want a little bit of a bigger screen here. For the balancing, you go through, make sure everything is even on both sides. I have 1K on both sides, but the F's are the only things that are off. There's 2 on the left on the reactant side, so I need 2 on the product side. That is also going to change the amount of potassium that I need on the left. And if you want, as a placeholder, you can put 1s in by the zinc fluoride and the zinc on the product side. So in this case, just like above, we have 2 starting amounts. We have, oh no, oh, there we go. Holy cow, I thought that was going to be a whole thing. Oh, it kind of is. I can't get to the yellow. I guess it's not too big of a deal. Holy cow, what is that? Sorry, all. I don't know what's going on. I guess we're doing those. So we have 8 moles of potassium and 8 moles of zinc fluoride. Now, what separates this type of problem, a limiting reactant problem, from a problem like this up here is that you notice up here, we only start with one quantity or amount of something. So then it's just a regular Stoich problem. But in this case, because we have 2 amounts to compare to each other of our reactants, right? And our reactants are, and I do not know why this is not allowing me to pick colors. That's a whole thing, huh? Because we have 2 to compare, right? This is a reactant and this is a reactant. We have to make sure that we figure out which one's limiting. So we only do the limiting reactant. Now notice, I start with moles of each of these, so I don't have to start with mass, which is nice. Again, you have to be able to read the problem, and that is the skill that we are using to be able to know when we need to do a step or not. So what I do is I start with the amounts of these substances. You'll see that, and we told a couple of you to change these to moles. Really, it doesn't matter necessarily. I'm going to keep it in grams, and I'll just let you know where you would have stopped in the other direction. But we first need to figure out the limiting reactant. So I have 8 moles of potassium to start with. Right, and I'm going to figure out grams of zinc, right? And this is the product that I want in the end. So how about I highlight that a different color, which we can use now. And of course, mole to mole is just going to use the coefficients, right, that we got from the balanced equation above. So I'm going to zinc. So that would be 2 moles of potassium for every 1 mole of zinc, and I'm going to go one more step. Now, we originally on the key and stuff, we stopped there because we changed this to moles in the end. You can do it whichever way. This is going to actually help us with part B when we talk about percent yield, so that's why I'm going all the way to grams. So this is a mole A to gram B problem up here, and we're going to do another one in a sec. And I know that moles of zinc should be equal to 63. Whoa, that's not right. I have a periodic table here because I'm a chemistry teacher. I always have one on me. Zinc is 65.39. So 65 grams of zinc, right? Now, the cool part about this is that when I do the exact same setup, I'm going to do it with the other amount of reactant, which is the zinc fluoride. So I also start with 8 moles of zinc fluoride. Whoa. And now I do the exact same thing. I'm going to try to see how much of the same product that I can make based on the starting amount of that. So that's 1 mole of zinc fluoride for every 1 mole of zinc. And the last step and a half are always going to be exactly the same compared to each other because you are trying to get to the same end to be able to compare those values in the end. So you'll see that with this substance here, I am going to the same product. So those parts of that should be the exact same values, right? The only thing that changes is whatever we start with, whether that's moles in this case or like grams in another case. So I go through and I do this math, and now I'm going to do this in the calculator here just so that you can kind of see me do it. There we go. 8, so I'm going to do the top one first. 8 divided by 2 on the bottom, and then times the 65.39. That's going to give me 261.56 grams of zinc. And then I'm going to do the same thing with the equation below. That's 8 moles of the zinc fluoride times 1 divided by 1. That's a skip step. And then times 65.39. And we get actually 523.12 grams of zinc. Now, what I did here is similar to what I just did up here with the bacon, tomato, and lettuce, right? Whichever one produces the smaller amount, that's my limiting reactant, because that's limiting the amount of product that I can make. And in this case, we look and compare those values. I can see that this is going to be the amount of zinc that I am able to actually produce. And whichever one produces that amount is what we would call the limiting reactant, which means that this, not just 8 moles, but actually zinc fluoride, that much of zinc fluoride is the excess reactant. So what we just did was we figured out, hey, the starting amount of substances that I had, well, that ran out first, which limited the amount of product that I can make in the end, and that's why we call it the limiting reactant. Which means that there's a little bit of that 8 moles of zinc fluoride left over, so we're going to actually figure out how much was left over here in a second. So limiting reactant, we just figured out that it was potassium, and the excess reactant was the other one, which was zinc fluoride. The amount of zinc produced in grams, well, we figured out that based on the starting amounts of those substances, we can only produce 261.56 grams of zinc. And then it asks for amount of grams in excess. Now, we know that the excess reactant, so I'm going to say the excess reactant is zinc fluoride, right? We know that. And we started with 8 grams, or 8 moles. So what I'm going to do is I am going to figure out exactly how many moles are in excess, and I can figure out how many grams are in excess after that. Because, of course, we start off with the mole unit, not grams. So what's cool about this is now that I know which one's my limiting reactant, that's the one that I kick off all of my problems with from here on out. Right? If I could ask, okay, how much KF is made? Well, I have to start with this because that's going to limit the amount of KF I can make too, so on and so forth. But stoichiometry also allows us to connect the reactants to each other. And that was a way that we did this before that, again, might have been a little bit hard to kind of grasp because there were different variables that we had to worry about. And this, I think, is a little bit more manageable for us just because it kind of makes it a little bit, it makes it make a little bit more sense in the grand scheme of things. So I'm going to take the 8 moles of potassium, and I am going to figure out, okay, how much of that other reactant can I make or do I need to be able to react? Because I evidently, since this is excess, I don't need 8 moles of this. That's too much. So I'm going to go using this, all right, my K, my limiting reactant. I'm going to be able to use stoichiometry to figure out, okay, just exactly how much of that zinc fluoride do I need? So I go and I say, all right, I have 2 moles of potassium for every 1 mole of zinc fluoride. And I'm going to stop there just because since we're given moles in the beginning, we're going to just use that value for now. So 8 moles, well, times 1 divided by 2, that actually tells me that in this reaction, I do have 8 moles of zinc fluoride to work with. However, I only use 4 moles of it, right? And so we compare this amount that we start with to this amount that we end with. And the cool part about this is that when we go down here, how many grams are in excess? Well, I know how many moles, and I can do one more conversion from moles to grams. So we started with, let's do it down here. So we had 8 moles. This is what we started with in excess. We found out it was excess. We found out just now that with our limiting reactant, we only use 4 moles. So used, we end up seeing that there are 4 moles of zinc fluoride, and this is left over. Right, but I do ask you for grams here. So we're going to go one extra step, and we're actually going to just do a quick dimensional analysis, and we're going to put the answer up here. 1 mole of zinc fluoride is going to be equal to a certain amount of grams of zinc fluoride, which is 65.39 plus whatever 19 times 2 is, right? 2 of those fluoride ions. So we end up with 103.39, 103.39, right? So this is how many moles were left over. We are just now converting to how many grams were left over. So 4 times 103.39 and 413.56 grams of zinc fluoride was left over in excess. And you're like, well, whoa, that's a lot of grams. I thought we only had 8. That's a small number. Well, remember, the mole it represents a very large amount of these things. So 8 moles is actually a lot. And 4 moles evidently weighs that much. So you could also say, well, how much would 8 moles weigh? And you do the exact same process, multiply it by the molar mass of the zinc fluoride. So that 827 right here, 827.12, I'll try to show you, is 8 moles. So we actually started with 827.12 grams of zinc fluoride. We only used 413.56, and of course that same amount is left over because it was exactly half. So that's pretty much the limiting reactant and some Stoich problems in a nutshell from the review guide. Last but not least, I'll try to make this one a little bit quicker. Percent yield is the efficiency of how well we did in terms of the lab if we were to actually take this reaction and do it. So we have actual over theoretical times 100 for a percentage. Well, a couple of items. The actual amount is the obtained amount from the experimental lab, right? So anytime you see experimentally, that means actual. They're interchangeable. That's like us going into the lab and actually doing this and then getting this many grams of zinc in the end, right? Well, the theoretical is the calculated amount of product using Stoich, right? So the calculated amount of product, right? We're talking about zinc, and we found the amount of zinc up here. That's that 261.56 grams. That's what we use Stoich to figure out in terms of how much we would produce. So that's, in theory, how much I should make. So this is our theoretical amount right here of product. But in a lab, a lot of things happen. There's a lot of variables, a lot of potential errors. This is the actual amount that we produce, right? So we didn't make as much, but we can figure out how efficient we were by taking those two values and comparing them, right? So there's our actual, 248.30. Divide it by what we should have gotten, and multiply by 100 to make it a percentage. I'm going to do that really quick just to make sure I get this correct for all of you. 248.30, leave the 0, divided by 261.56 times 100. And that gives us, math, decimal, that's a whole thing, 94.9 or so. So percentages, I'm usually good with just the tens place. So this is 94.9%. And the closer we are to 100, the better we did, because the more close to the actual theoretical, or the theoretical, I should say, the closer we were to the theoretical value, right, what we calculated. So that's pretty much this in a nutshell. Everything else, I think, is more so of the same type of problem like above. All right. So hopefully this helps. If you have questions, just reach out and let me know.